Hello everyone, welcome to lesson 2 of this AQA Astrophysics unit, A-level. This is all section 3, which is all the astrophysics part of it, which is normally at start of year 13. So this is for lesson 1, so you need to go back and look at the refraction telescope before you start doing the reflection telescope, which is what is here. This is the first bit, this is lesson 1. This is the bit I'm going to do in lesson 2. I might just pop on to give you a little bit of a taste of what's coming up as well. So we're going to use something called a Cassegrain arrangement for a reflecting telescope with parabolic, I'll explain what these are in a second, concave primary mirror and convex secondary mirror. We're going to do a ray diagram again, and also we're going to look at the relative merits of reflectors and refractors. Very common exam question in AQA, so I'm just going to talk you through that. So if you're a professional astrophysicist, this is the only telescope you're going to use. Cassegrain telescopes, this idea of having a reflecting mirror with another reflecting mirror, which is a convex mirror, and then comes through a hole in the back of the telescope here. You can see this here, and then comes to a lens or an eyepiece or even an eye. You can actually pop there as well. The 3 ingredients: primary, parabolic. Now this mirror, of course, it can be made very thin but also very light. You haven't got a whacking great lens sitting there. So actually this mirror can be very, very thin indeed, very flat, of course. These parts flat, I know it's a bendy bit here. Secondary's got to be convex, which is sitting in the middle of here. It's suspended usually by wires or by little sticks that are called a spider across here. And then you've got an eyepiece, which is a converging refracting part of it, but most of this is a reflecting one. This is what it looks like in real life in a telescope that you'd find on the top of a mountain or on a satellite or in your back garden if you're that keen. They come fairly small as well. So there's the parabolic section of it. We're going to draw this sort of thing up here because that gives a really exaggerated view, but this is more what you're looking. Incidentally, ignore the red and the blue. This has nothing to do with wavelengths. It's just to show the different waves are going. So this is what you're going to do. You're going to draw this part first as if it looks like a single mirror with a hole in there. So you've got to practice this view here. So in your notes now, just practice that view, that lovely sort of smooth parabolic concave mirror. Concave is like a cave. You go into a cave. Then draw this one here. This is a convex secondary mirror. This is the primary, this is the secondary. And then make these light rays cross here. Now, the examiners seem to like the idea of you crossing it here or here. They don't really like you having it crossing over here, not quite sure why. But nevertheless, it doesn't really matter where they cross, it's still going to work. I would make sure they cross there, just to keep the examiners happy. Okay. And sometimes this eyepiece is left out. You need it. Either put an eye there, so you can put an eye on the end, or put that eyepiece. And these are just the common things that are in the. There's quite a nice PDF that I'll include on the link on my channel to be able to make sure you can get that. This is all taken from a handbook that AQA produced a long while ago by Mr. Organ. What a fantastic name. Okay, so build it up and use a ruler for the light rays. Examiners are very picky about you not using a ruler because the light rays are straight. So build that up, stop the video now, just do that in your notes, and then make sure it looks like the image that we had at the start. So just moving on, this is what real Cassegrain telescopes look like. This is the Gemini on top of Mauna Kea. This is the now defunct JCMT, James Clerk Maxwell telescope, which is a submillimeter telescope. And the reason I did it is you can see the hole there, and you can see the hole there in the middle of these mirrors. Here's the secondary up here. That's remember a convex mirror, and here's the secondary there. You can just see it there reflecting back down and through. So light rays comes out from space, going up and then through the hole. In this case, it's going to come through when this is open, of course, through, up, and then down through it. Down here somewhere is a lot of CCDs and computing. Oh, there's me. Look at me. Look at that lovely hair. It was trendy when I was 25. All right. And this is what's at the bottom of the telescope, Scuba, which is the satellite that I worked on. There's the secondary mirror. I took a picture up there, nearly 10 years before I started teaching. And there's the back of the mirror. You can see how big it is. This is a huge 15-meter telescope. And then, thankfully, I've just chopped off that picture of me and my face. Lenses can suffer from spherical aberration. Aberration, 1B, 2Rs, very commonly mistaken for the same sort of thing as abbreviation, but it's aberration. So, and then Remember that language? Multiple focal points cause indistinct images. Okay, multiple focal points cause indistinct images. In this case, spherical aberration. The lens, as you can see at the top, calls it, but also mirrors just beneath my head here. In other words, the ray on the outside focuses it too short, the ray from the inside focuses it too long. So you end up with spherical aberration causing multiple focal points, which cause indistinct images. And that's a bad thing. Okay, this is a pretty incredible photograph, really. This is the telescope, refraction telescope, one of the last large refraction telescopes that was constructed in the United States. And there is a very famous group of people. You probably can't see the detail, but you probably recognize that chap there. That's Albert Einstein, because this is one telescopes that was the idea of general relativity. And may I note the number of female astronomers that are in this photograph back in the 1920s. It was great. Astronomy was a real quality in astronomy. Henrietta Leavitt, for instance, led the world in giving the distances to galaxies that Hubble discovered, and her work with Hubble basically secured the idea of the expanding universe, and it's fantastic to see. They often were not credited in the exam papers, but nevertheless, see it. It was started there in the 1920s, and the female astronomers here have always been represented all the way through the years. Fantastic breakthroughs. Of course, not really celebrated, and that's why I'm celebrating it now. Okay, so that's the first part here. So that's the ray diagram showing path rays through the telescope to the eyepiece, and then the Cassegrain arrangement. So that's what we've done so far. So let's move on to this relative merits of reflectors. So there's going to be a fight between refractors and reflectors. Who's going to win? I think we know who. I've already given you some hints, but you need to be able to articulate why one of these is better than the other. So if we had the fight, the reflectors would win, but nevertheless they would give ground in some areas. And so let's start on the refractor side. So refractors are going to be very large. They're going to be heavy. They're going to be very long as well. They have this as well. This is chromatic aberration, because you can see the red line on the outside of that dove there and the blue on the inside. It gives that chromatic aberration. Spherical aberration also starts looking like this. It starts looking blurry because multiple focal points cause indistinct images. Now, Cassegrain reflectors, of course, can be made very large indeed, and you can support mirrors here much larger than a lens. You wouldn't get a lens this large. They can also make them quite short also. What's wrong with these things? Well, these things here, these support the secondary mirror, and it can end up giving these little spikes in an image. This is a simulated image I've got here, but nevertheless you can get spikes. They're called spiders, and that means that they can get in the way, so that can reduce the amount of light that's coming in, which is bad, but really not bad compared to that. You can send these things into space because they're light, they can be short, they can be very powerful, but you still get the spiders. These things, you can't put them in space, you don't build them anymore because they're way too heavy, way too massive. Yes, you can reduce some light into it by putting it in a tube, but you can do that for these as well. They just don't do that here because it's better for air stability around telescopes. Just recapping what those pros and cons are. Your glass Galilean refractors, you can protect them, you can correct for spherical and chromatic aberration, but really there's an awful lot on those as well. Pros can be enormous, large collecting areas, no chromatic aberration on B2Rs, and then greater resolving power. We'll come back to resolving power. Basically, you can resolve smaller things if you have a bigger telescope. Cons: tiny light loss. Still need some refractors at the eyepiece, and you get diffraction from the spider. And I don't mean the little crawly thing that runs across the front of the telescope. What I do mean is the light sticks, basically, that hold up the central secondary mirror. Okay, so that's comparing the two. Just to recap what we've got so far: Cassegrain telescope, you're going to be able to construct that chromatic aberration, 1B2Rs, multiple focal points, cause indistinct images. Same with spherical aberration, you need to be able to draw that as well. You need to be able to compare reflection and refraction. Your normal refraction telescope, in normal adjustment, you need to have 3 rays coming through, 3 rays in, central one through the middle, and then coming out the other side, showing magnification and showing lots of other bits and pieces as well. Angular magnification, which is your f0 over fe, or your ratio of your angles, angular size, size of the object way off, divided by the distance from your nose or your eyes to what it is, and that gives you in radians. Remember, so that's a recap of what we've learned so far. Okay, and just to go through this again, we've gone to the next part. My apologies. This is our next part. We're going to be looking at single dish telescopes and large diameter telescopes, and I'll come back to that idea of angular resolution in a second. So, carry on to lesson 3. This is lesson 3. Go back, practice the Cassegrain, and practice comparing refraction and reflection. Okay, and hopefully you heard that little bird tweeting to say we're finished.